Hello everyone, welcome to this video. My name is Amir Senahari. I'm a Google Earth Engine expert. In this tutorial, I'm going to show you how to deal with MODIS Ocean product, a valuable product that helping us to get information regarding to the water surfaces. So let's go to the Earth Engine code editor environment. First of all, we need to identify the region of the interest. And as we are working on water-related parameters, we need to select a region that is sea surface, ocean, or a big lake, or something like that. For example, I'm going to have focus on Persian Gulf in the south of my country, Iran, as you can see, using the drawing or rectangle tools available here. Persian Gulf selected by the rectangle, just like that. And also we can expand the study area to the Gulf of Oman, as you can see, a wider region to see the variation of different parameters in different regions and helping us to get a better insight about the different factors we're going to estimate in the visualization process. So next, in order to have focus on the study area, first I want to start code with map.center object. Map.center object for the geometry. Actually, we need to have focus on the study area when the code runs. As you can see, when the code runs, the display focused on the region of the interest that is already drawn here. So in the next step, we need to call MODIS Ocean product. So here, make a new session using the / called MODIS Ocean product. It's a simple description about what I'm going to do in this step. So through the search places and dataset, just type MODIS Ocean. And as you can see, various products available regarding to the MODIS application in the water surfaces, and one of them is Ocean Color SMI, standard mapped image MODIS Aqua or Terra. It depends on the temporal extent. Actually, as you know, the Terra data available since 2001, Aqua available since 2003 or the mid of 2002. I prefer to use Terra satellite data because Terra and Aqua, both of these satellites carrying same sensor, and the MODIS sensors in these satellites are almost same without any clear difference. Import it into the code, and now you can see that we have it as image collection in that menu. So make a new variable to assign image collection. So the variable is MODIS equals to, now I'm assigning image collection to a MODIS. So then this product is daily, and for example, I'm gonna to call daily data only for 1 year in this step. Through the dot filter date, you need to narrow down your data to a specific year, for example 2019 or 2023, for example, the last updated. And then through the print, you can check all available MODIS Ocean products in this period. So as you can see, unfortunately, no one of the MODIS products available for 2023 yet. And also we go to 2022. And now you can see only this data is updated until the late of 2022. But it's no matter because you can use this product from 2001 to 2000, for example, to 2022 at least. 22 years data for the time series analysis for the water related factors. And as this data is daily, we are calling over 5,000 image that's in contrast with the problem in the Earth Engine platform when we want to print more than 5,000 elements, 5,000 elements in this environment. For example, I try for 2020 to 2022 only for 2 years. As you can see, over 600 images are available here, and each image or each element, including 14 elements or 14 bands, One of them is chlorophyll A, helping us to get chlorophyll variation over the sea surface. And the next one is, if you go to the data description, actually, in the bands here, you will see the description for each band separately, and that would be a better. And as you can see here, mentioned that these data are only available since the 2000 until the February 2022. So the first is chlorophyll A, the first band, and the next one is normalized fluorescence line height, actually. The NFLH, or fluorescence line, actually helping us to find the density, or the density and distribution of phytoplankton over the sea surface, and also it's a factor attributed to the biomass production actually in the sea surfaces. And the next one is POC, that is particulate organic carbon in the water, and also the water reflectances also available in different wavelengths. And the last band is sea surface temperature, that helping us to measure the temperature of the water surface. So this product is specifically designed for the water surfaces, and also you will not be able to use this product for example, non-water regions such as the land regions or land areas. And also now I'm gonna show you how we can use this product in the Google Earth Engine platform. And also it should be mentioned that the product spatial resolution is around 5,000 meter or 5 kilometer, unlike the other MODIS products available in 250 meter to 1 kilometer. This product provided information with 5,000 meter, and also it doesn't matter if the spatial resolution is coarse, because we have no such big variations over the sea surfaces. And as the sea surfaces are very homogeneous, and the changes are really gradual, and no need to have very detailed information, unless we want to work on the for example, coastline region. Maybe we face with some problems due to the coarse spatial resolution. Okay, let's back to the code, and now I want to show you how we can get this kind of information separately, and how we can do the mapping for each band. So here just I'm trying this code for only 2 years, but you can extend the time series from 2000 to 2022, and I will show you in the next step how we can do it. And now I want to produce different maps to show you how to visualize the existing bands. So the first, we want to do mapping for bands. In this step, I want to call each band separately and then visualize them through the map.add layer. The first, I want to make a map for the chlorophyll. For example, just write the name of the variable, including the variable that including the ID of image collection, or image collection ID for the MODIS Ocean product, and then you throw the .min. You can get an average from all bands per pixels over 2 years, and then through .select you will be able to select your target bands. That here is chlorophyll A, the first band, and then through the map.add layer you will be able to visualize the chlorophyll image that is clipped according to the border of the rectangle that's already defined, and then leave the visualization parameter empty, because we don't want to do the final visualization for the papers in the Earth Engine. And then the layer name here is chlorophyll, and use the false at the end to avoid automatic visualization or automatic loading of results, because it reduces the speed of processing clearly in the Earth Engine. So save your code and run it again. Now in the layers we have chlorophyll band, the average chlorophyll values in each pixel for the years between 2020 and 2022. So here, by increasing contrast, for example 90%, you can increase the visual characteristic, and also you should check if any scale factor is available or mentioned or not. Hopefully there is no scale factor here, meaning that you can just call this data immediately and then show it through the map.add layer, and no need to apply any scale factor. So, and now still we have a problem in visualization parameters. Let's try with the other techniques available for the stretching here. In the chlorophyll product, the higher values in the chlorophyll bands, the higher values, higher chlorophyll, and lower values, the lower chlorophyll. I'm still waiting for the stretching technique to be applied on the range of values, and then you need to click on apply to see the variations better. So now click on the variations. Now you can see that here in the coastline regions, the lighter color showing that higher amount of chlorophyll available there, and also as much as we get distance from the coastline, we go further, you can see that the darker regions showing lower chlorophyll in this region. Again, I try for another method to increase the contrast as much as I can. Now it's better, and you can turn the background from map to satellite to see the value variations better. Through the inspector, you can see that the white region is showing higher values, meaning that higher chlorophyll available here, and also the darker region, lower chlorophyll values, and meaning that lower chlorophyll available in such regions. And also it's very, very helpful. And what this is this is an average image. You can get maximum chlorophyll values per pixel, and also you can the median values per pixel, or you can have the minimum value per pixel. It's very, very simple and easy to use technique to do the visualization in the Earth Engine platform. So imagine that now we want to repeat this process, getting average and visualization for another band. Instead of chlorophyll, here I want to show the NFHL band, NFLH band, that is normalized fluorescence light height, that showing the phytoplankton existence in our area or in the region of the interest. Select the band name and make a new variable. For example, phytoplankton equals to call the MODIS data first, and then get the average. But this time, instead of chlorophyll, we want to have fluorescence band. So then through the map.add layer, you will be able to show the final result same as chlorophyll band. But this time, just the name of input changed. Again, clip it based on the geometry, leave the visualization parameters empty, and the name is phytoplankton, and then use the false at the end. Run the code. Again, we will have one band here with phytoplankton name that's showing the amount of fluorescence emittance in different regions. That is a proxy for the for the existing phytoplankton in different region. and also it is an index to assess the biomass production in the open seas. So, and again you will see, or you can see, we can increase the amount of enhancement, amount of contrast through the stretching technique available here. As you can see again, the fluorescence emittance is higher in the coastline regions, and as far as we go away from we come away from the coastline, the amount of the phytoplankton reduced. The highest concentration of the phytoplanktons are in the coastline regions. And when I click by the inspector here, you can see that the lower value of fluorescence in the inside, but in the corners and also in the margins close to the coastline, a higher fluorescence value and higher chlorophyll value detected. So now in the next step, I want to try this method for another band, or repeat this method for another band that is the particulate organic carbon, and also POC is the band name. For the target band, make a new variable again, just write POC. As you can see, the same technique repeated, only the input bands changing. MODIS mean, get the average, but this time only select the POC band, or particulate organic carbon. So then through the map.add layer, you can see we can get the POC bands here, clip it based on the region of the interest, leave visualization empty, the band name particulate organic carbon, and then use the false. Run the code again. Again, you will see a new band here. Increase the contrast through the 90% enhancement. After range of value updated, apply it. If it doesn't work, try with the other techniques. So now you can see that the distribution of particulate organic carbon is a little different than what we saw in the phytoplankton and chlorophylls. As you can see, in the south side of Persian Gulf, you can see that we have higher concentration of particulate organic carbon. So the higher values, higher POC, and lower values, lower POC. And also this is a simple interpretation about what you are seeing in the image. It's very simple and easy to use. No need to do any further calculation, even any scale factor. Just you need to call, select your band, and through the map.add layer, show the final results. So this is a simple mapping technique for the all bands. And next, I'm gonna show you how you can do the time series analysis for this region. For example, in the first step, maybe in your application you want to download chlorophyll images or sea surface temperature images for 1 year or a longer period of time. Now I'm gonna show you how you can download your desired images in a stack format and use it in your desktop software. Just make a new variable. Now here I want to show how to do stack raster layers. It's another applicable or popular method in the Google Earth Engine platform when we want to download couple of raster layer for a specific period of time. For example, I'm gonna download sea surface temperature for the winter time with the raster format for the further processing in the desktop software, and I want to use it in the desktop software for the further processing. just make a new variable, SST equals to sea surface temperature. So from the MODIS dot select your desired band. As you can see, another band available here is SST or sea surface temperature, that's showing the temperature specifically for the water region. SST, and then through a calendar range, I can call only SST images only for one specific month or only for a period of time. Through the dot filter, make a new filter inside Earth Engine dot filter dot calendar range. For example, I'm just gonna download all SST bands for the January. The start month is the January and the end month is also January again, and the unit should be months, meaning that we want to download only images related to the January or images collected in the January. Now print the result. You will see the SST or sea surface temperature images, 62 images available for 1 month. In the feature you can see the images, and then I want to make a stack from the SST, new variable SST stack equals to SST.toBands. .toBands is a useful method that's allowing us to make a stack from the input images. And again, print SST stack. In the previous time, you saw that we have one image collection in which 62 elements are available. But this time, when the code runs, you will see that we have one image with 62 bands instead of one collection with 62 elements here. This time we have one image with 62 bands, and also the dates also available for each band. Each band name actually representing the date of that image, and also it's very useful. And also through the map.add layer, you will be able to see all the images when they are stacked in a single file. Here I want to see a sea surface temperature stack that is clipped based on the geometry. Leave the visualization empty, and this time the layer name is SST stack, and use the false at the end and run the code again. So here you can see the SST stack is created, but sometimes the image is cloudy, and also maybe we have some missed pixels. It is not it is not weird in this optical satellite images, specifically in the winter time. For example, you can see that all images available here, and you can select one of them, and then through the apply you will see the image for that bands. The darker region showing the lower temperature, and the lowering temperature, and brighter region or white region showing the higher temperature in the water body. For example, in Gulf of Oman, you will see that the temperature is higher than Persian Gulf, and also showing the temperature differences very clearly and also easily to understand and interpret. So imagine that now you make this stack layer and you want to download it. Type export .image to drive. So the first argument, image, equals to SST sea surface temperature that is stacked, and clip it based on the region of the interest. The next argument, description, equals to the output file name, SST MODIS, or whatever you want. And scale Spatial resolution is 5000 meter. Scale is also 5000. Region of interest, geometry, and CRS, spatial resolution. If you want to get output with output coordinate system, if we want to get, if actually the CRS is coordinate system, and if you want to get coordinate system for the output image, set EPSG 4326. This is a code that used for setting coordinate system to WGS 84, and for all around the world you can use this. The maximum pixel in each image should be equals to 1 if 13, and also the next actually you can set a define folder to save your data in. For example, the folder is test here, and run the code. As you can see in the task SST MODIS is available. Click on run and again run, and now we are waiting until the process of saving in Google Drive is over. Once the product stored in the Google Drive, the tab color turns to the blue, same as previous one, and then you can pick it up from the Google Drive. So that is the methodology we use, or that's the scripting technique that we use to get export time series raster images from the Google Earth Engine platform. So this data, as you see that, this data is daily, but maybe you want to get output from this data with monthly, weekly, or even seasonal format. And also, if you watched my video, my previous video in my YouTube channel, I always use the temporal collection function that is developed by the Google developers and helping us to produce multi-temporal collection in the Earth Engine platform. So it's a little difficult for the beginners, but if it is difficult for you and you cannot write this code by your own, you can use my own code. It is available below the video in the description box. You can use it. You can use my code, copy and paste this part of code, and get your desired multi-temporal collection. So now I want to show you how we can make temporal collection in the Earth Engine platform. But it is one of the most repeated technique I used in my tutorials. So now we need to make a function first. Its name could be anything. For example, here I use temporal collection name, and this function including couple of arguments. The first is the collection of input images, and then start date, and then count the number of output images we expected, and also the interval, the temporal difference between output images, and then the unit of time for the time series analysis. First, in the body part of function, make a sequence, make a list according to the number of output images that is expected. So here make a variable sequence equals to Earth Engine .list.sequence. Three main arguments here, two main arguments we have here. The start is 0. The list started from the 0 row to the number that is already set for the count, Earth Engine .number count. So as we are starting from 0, we need to subtract the count number from 1. Remove the rest of arguments. Next is origin date. The origin date helping us to convert the start from a string to the date format, because we need to import the start date with a string format. Earth Engine.date get start and convert it to the date structure. Now we need to return this list with the collection or image collection format. Write return earth-engine.image collection sequence of we have the list in the image collection format, and now in each row of the list through the map we make a function that each row considered as an I, and we want to estimate the start date and end date for each row separately here. Make a new variable as start date equals to from origin date dot advance. So here the delta or the temporal difference should be identified or replaced by the interval earth-engine.number interval, apply it on each row that is defined as I, and the unit is unit, no need to change. Again the same code for end date, just with a little change. Again origin date dot advance earth-engine.number interval dot multiply. So here we need to select one unit after I, earth-engine.number I dot add one unit after. That's it. Finally, function returning input collection, already defined here, to a specific period of time through that filter date. So in this period we need the period or time span identified through the start date and end date. Start date and end date. In this period we want to get average for the output, and for the output further processing we need to set system time start and system time end. System time start coming from start date with millisecond format, and also throw that set system time end defined, but this time end date dot millisecond format. For the time series analysis we need these properties, and also it's essential for the further steps. So now the function is created, and I want to apply this function to available images for 2 years and convert them, for example, to weekly format. So here make a new variable weekly equals to temporal collection is our function. So here we have couple of arguments that should be replaced by different factors. Instead of collection we import here, as you can see, we want to convert MODIS variable that is called for 2 years from daily format to weekly. Replace collection by MODIS. The start date should be same as the start date for MODIS variable that is 2020, and the count is the number of outputs expected. Here we aimed to get weekly images for 2 years. Each year including 52 weekly images, or each year consists of, for example, 52 weeks, and for 2 years we will have 104 weeks. So 104 1 week interval should be 1 and unit should be week. Here print weekly data As you can see, 104 images is available. All the bands have the value, but some of the bands missed because of the missed value in that date for some specific dates or some specific periods because of the cloud cover or noises or something like that. Maybe we missed some bands and also or we missed some images for some dates, but there is no problem in this regard. And now you can select your desired band and download it, and also you can select your desired band and plot the variations in your region. For example, I want to plot chlorophyll changes with weekly interval from 2020 to 2022. Just write print, inside print, type user interface chart image.series. Here we have arguments. Instead of image collection, input weekly. Instead of the region, geometry. Instead of reducer, if you want to get average chlorophyll variations over Persian Gulf and Gulf of Oman, you can use average reducer. First engine.reducer.min. If you want to get maximum values, max, minimum value, mean. If you want to get the median value, median. It depends on your goal. Average, and then scale is 5000 because the spatial resolution is 5 kilometer, and X property equals to system time start here. System time start. Run the code, and chart is under generating, and also the SSD MODIS is saved into the Google Drive, and through the opening drive you can go there and download your final results. So, and now all the bands plotted here, but we need to select the chlorophyll bands before visualization that is missed in my code. Through that select, you will be able to select your target band. The target band here is chlorophyll A. You can see the chlorophyll A band name is available here. Copy and paste it, and then a new chart is generating, and here you will see the chlorophyll variations in the average chlorophyll variations in your region of interest over Persian Gulf and Gulf of Oman. You will see the variations, the higher chlorophyll for some dates and lower chlorophyll in different dates. And interpretation of these results is actually, it's not my expertise, just I'm remote sensing and Google Earth Engine expertise. And here I'm here to show you how to work with this data. If you want to have interpretation about the result, you need to have information about the sea surface factors such as chlorophyll, particulate organic carbon, or sea surface temperature. And also you can use this plot with weekly format for example, temperature. Here, just repeat the code with a little change. This time import SSD as a band name. Yes, the SSD is the sea surface temperature band name. And now you will see the temperature variations or in this area that you can see it has seasonal fluctuation that is expected, and also it is based on the degrees Celsius available here. And finally, you will be able to download the plots through the download CSV in Excel format, and you can use the Excel formats or CSV formats in the Excel software or Python programming language for the further analysis. So I hope you like this tutorial as much as I do. If you had any problem regarding to the programming techniques, first of all, compare your code with my own example that is attached below the video in my YouTube channel. If a problem still exists, you can contact me or reach me out through LinkedIn or through my YouTube channel, and I will try to help you to deal with this data easily in the Earth Engine platform. Thank you for watching me, and also you hope like this tutorial.